right, let's jump right into one of the most exciting frontiers in medical imaging today, generating synthetic CT scans directly from MRIs. If you are anywhere in the world of medical physics, AI research, or radiotherapy, you already know this is a massive deal. Today, we're going to map out the evolution of this technology and break down the 9 major deep learning models that are completely reshaping modern radiotherapy.
Here's our roadmap for this explainer. We'll start with the synthetic CT revolution, then move through foundation models, the adversaries, deep networks, the cutting edge, and finally wrap up with a head-to-head final comparison.
Okay, Section 1. The synthetic CT revolution, bridging the gap between MRI and CT.
So you might be wondering, since MRI gives us such stunning, clear images, why bother generating a synthetic CC at all? Why can't we just jump straight into an MRI-only workflow for radiotherapy and skip the CT scan entirely?
Well, here's the catch. MRI gives us beautiful, highly detailed soft tissue contrast. That is absolutely amazing for pinpointing exactly where a tumor is located. But it fundamentally lacks physical density information. CT scans, on the other hand, provide electron density and Hounsfield units, which actually measure that physical tissue density. We literally need those metrics for accurate dose calculations in radiotherapy. You just can't safely plan a radiation treatment without them. So synthetic CT steps in as the ultimate bridge, using AI to predict those CT values straight from the MRI scan.
Moving right along to Section 2, Foundation Models. We're building the baselines here with UNet.
Let's look at our first 2 models, Standard UNet and Attention UNet. Think of these as our foundational baselines. Standard UNet is your classic encoder-decoder CNN. It takes either an MRI or a cone beam CT as an input and spits out a synthetic CT, making it a fantastic, reliable baseline for research. Then we have Attention UNet, which is an attention CNN. It takes purely MRI inputs to output a synthetic CT. This one really excels when you're dealing with complex anatomy like the head, neck, and pelvis.
So how do they actually process all this data? Well, a standard UNet uses an encoder to pull features from the MRI and a decoder to reconstruct the CT, passing info through what we call skip connections. It's simple, fast, and super stable. The downside is that it can sometimes output slightly blurry images when the anatomy gets really complex. Attention UNet fixes that blurriness. It literally uses attention gates to zero in on important anatomical structures, creating importance maps. You get way better edge and bone preservation this way. But as we always see in deep learning, there's a trade-off. It demands a significantly higher computational cost.
All right, Section 3, the adversaries. Let's introduce GAN-based models.
This brings us to Pix and CycleGAN, which both rely on generative adversarial networks, or GANs. Both models output a synthetic CT, but they have completely different input requirements. Pix is a conditional GAN, meaning it absolutely requires perfectly paired MRI and CT images of the exact same patient in the exact same position. CycleGAN? That's an unpaired GAN. It can take totally independent, completely separate datasets of MRIs and CTs. And this represents a really fascinating trade-off. In both of these models, you have a generator creating the image and a discriminator critiquing it, kind of like an art forger and a detective constantly trying to outsmart each other. Because Pix relies on perfectly paired data, it gives you incredibly sharp boundaries, which is ideal for MRI-guided radiotherapy. But honestly, GAN training can be pretty unstable. CycleGAN gets around the paired data problem by using a clever trick called cycle consistency loss. This is a game changer for hospitals that just don't have perfectly aligned scans. The limitation, though, is that without that paired grounding, there's a higher risk of the model basically hallucinating anatomical inaccuracies.
Next up, Section 4, Deep Networks. We're scaling up with DenseNet and ResNet.
Now we're getting into the heavy-duty architectures, DenseNet and ResNet. These are designed to extract features way more efficiently and push for true clinical quality image translation. DenseNet is a dense CNN that takes an MRI and outputs a synthetic CT, and it's a real lifesaver when you only have small datasets to work with. ResNet, or residual CNN, can take either an MRI or a cone beam CT to generate the synthetic CT, and it is pretty much the go-to architecture for getting clinical quality results on massive datasets.
It's super interesting to see how these 2 networks handle depth differently. You know how as neural networks get deeper, they tend to forget earlier information. It's that classic vanishing gradient problem. DenseNet tackles this by using dense connections that allow efficient feature reuse across every single layer, which really improves convergence. The problem is, passing all that data forward eats up massive amounts of memory. ResNet takes a totally different route. It uses residual blocks and shortcut identity connections to bypass certain layers, entirely dodging the vanishing gradient issue. This lets you build incredibly deep networks with excellent image quality. But yeah, it's going to demand larger GPUs and much longer training times.
So if we take a step back and look at the timeline, you can really trace the evolutionary arc here. We kicked things off in the first generation with our fast, simple, but slightly blurry UNet baselines. Then we leveled up to the second generation, bringing in the sharp boundaries of adversarial GANs and those highly reliable deep CNNs like ResNet. And now we are squarely entering the third generation, where the game is all about global anatomical context and just absolute extreme realism.
Which brings us to Section 5, the cutting edge, diffusion models, and transformers.
Let's start with diffusion models, which take an MRI input and generate a synthetic CT output. These things achieve a level of realism that is just unparalleled, and they do it through a surprisingly stable three-step process. First, forward diffusion intentionally adds pure static noise to the image, gradually. Second, a network learns to predict that exact noise, conditioned on the patient's MRI. And finally, reverse diffusion takes a frame of completely random noise and systematically denoises it step by step until you have a pristine, hyper-realistic synthetic CT. The anatomy preservation is incredible. The catch? You are going to need some very expensive GPUs, and the inference time is notoriously slow.
Meanwhile, vision transformers completely flip the script on architecture. Taking an MRI input to output a synthetic CT, they don't scan pixel by pixel like a traditional CNN. Instead, they chop the MRI into patches and use self-attention to grasp global anatomical relationships. They are amazing for multi-center research on huge data sets. And actually, this exact breakthrough paved the way for hybrid models, architectures that mash up CNNs and transformers. Taking an MRI input, these hybrids create the ultimate state-of-the-art synthetic CT output for future clinical AI systems.
The synergy here is really what you need to understand. Vision transformers give us this incredible global context through patch embedding. Basically, the AI understands how the whole body fits together rather than just zooming in on a local edge. But they kind of fall flat if you don't have massive data sets. Now, hybrid models? They combine the CNN's talent for seeing fine local details with the transformer's big-picture understanding of the global anatomy. The result is true state-of-the-art accuracy. They learn everything perfectly. But I have to warn you, the architecture is incredibly complex to build out and demands seriously long training times.
Okay, let's wrap this all up. Section 6, final comparison. How do you choose the right model?
Pulling this all together into one master view, you can really see the distinct trade-offs across all 9 of these models. Notice how the image quality radically improves as we move from basic UNets all the way to diffusion and hybrid models. But that premium quality almost always costs you training speed and implementation complexity. At the end of the day, you have to choose the right tool for your specific environment. It really all comes down to whether you have paired data, how much GPU horsepower you're working with, and whether you care more about rapid speed or absolute pixel-perfect realism.
Ultimately, every single one of these advancements is pushing us toward a reality where AI seamlessly powers MR-only workflows. By accurately predicting Hounsfield units directly from an MRI, we can spare patients from extra radiation, we can totally streamline hospital workflows, and we can finally enable highly responsive adaptive radiotherapy. So, I'm going to leave you with this thought. As these models, especially those cutting-edge hybrids and diffusion networks, continue to get faster and more accurate, how soon do you think this technology will completely eliminate the need for standard CT scans in treatment planning? It is a fascinating question, and one the medical physics community is answering faster than ever before. Thanks for joining me on this explainer, and I'll catch you next time.